Hello friends, welcome to my lecture on Laplace and Poisson equation. First we will consider the solution of Laplace equation by Fourier series method. We shall see that using the method of separation of variables for solving partial differential equations, to be able to fit certain boundary conditions, Fourier series methods have to be used, which lead us to the final solution being in the form of an infinite series. Let us consider the Laplace equation in two dimensions. Uxx plus uyy equal to 0, where 0 is less than x less than pi, 0 is less than y less than pi, and the boundary conditions are when x is 0 for all by u0 y equal to 0, when x is equal to pi, y is for all by u pi y is equal to 0, then ux pi equal to 0 and ux 0 equal to sin square x. And now let us consider the Laplace equation in two dimensions. Uxx plus uyy equal to 0 for 0 less than x less than pi, 0 less than y less than pi, with the boundary conditions u0 y equal to u pi y equal to ux pi equal to 0 and ux 0 equal to sin square x. So you can consider this rectangular plate, this is your x axis, this is y axis. Here we have y equal to 0, here x equal to 0, here x equal to pi, and we have y equal to pi here. So at this end y equal to 0, okay, we have ux 0 equal to sin square x. So here we have ux 0 equal to sin square x. This end and this end, these three ends are kept at 0. I mean, if you call u as a temperature, these three ends are kept at 0 temperature. We have to find the steady state temperature in the rectangular plate at any point x y, where 0 is less than x less than pi, 0 is less than y less than pi. Okay. So what we will do, we will solve this partial differential equation by using the method of separation of variables. So let us put uxy equal to xx into yy in the given second order differential equation. Then we have x double dot into y plus x into y double dot x into y double dot equal to 0. Okay. So uxx becomes x double dot by uyy becomes x by double dot equal to 0, and when we divide by capital X into capital Y this equation, I get x double dot over x plus y double dot over y equal to 0, or I can write it as x double dot over x equal to minus y double dot over y. Okay. So now left hand side is a function of x only and right hand side is a function of y only. Okay. Both are equal, so they must be equal to a constant, let us say k. So we get two ordinary differential equations of second order, x double dot minus kx equal to 0 and y double dot plus ky equal to 0. Okay. Now there are three cases, k equal to 0, let us take k equal to 0. So k equal to 0 now means x double dot equal to 0, and k is equal to 0 gives y double dot equal to 0. X double dot equal to 0 means x is equal to ax plus b. Y double dot equal to 0 means y is equal to cy plus d. Cy, okay, cy plus d. So what we have, so this means that uxy is equal to ax plus b into cy plus d. Okay. Now let us use the boundary conditions. When x is 0, u0 y equal to 0. So u0 y equal to b times cy plus d. Okay. u0 y is equal to 0 gives b equal to 0 or c equal to d equal to 0. Okay. So this gives you b equal to 0 or c equal to D equal to 0. Now if C is equal to D equal to 0, then Y is equal to 0. Y is equal to 0 means U is equal to 0. Okay, so trivial solution, and therefore we shall not consider C equal to D equal to 0. Let us take B equal to 0. If B is equal to 0, then what we will get? If B is equal to 0, then U x by is equal to A times x plus into C by plus D. Okay. Now again U pi y equal to 0. So U pi y equal to 0 means again either A equal to 0 or C equal to D equal to 0. C equal to D equal to 0 is not possible, so A must be 0, and when A is equal to 0, A equal to 0, B equal to 0. Okay, both give x equal to 0, this capital X equal to 0. So again we get a trivial solution. So K equal to 0 is not possible. Let us now consider the case K equal to mu square. K is greater than 0. Okay, so take K greater than 0, say K equal to mu square. Then what we will get? D square x over dx square minus mu square x equal to 0 means x will be equal to A e to the power mu x plus B e to the power minus mu x, and here K is equal to mu square means the auxiliary equation will be m square plus mu square equal to 0. So m will be plus minus I k, so we will have complex roots. So y will be equal to C times cos mu y plus D times sin mu y. Okay, what we will get? So u x y will be equal to x x into y y. So A e to the power mu x plus B e to the power minus mu x into C cos mu y plus D sin mu y. Okay. Now let us see u 0 y equal to 0. So u 0 y equal to 0 gives put x equal to 0. So we get A plus B into C cos mu y plus D sin mu y. Okay. So either A plus B is 0 or C and D are equal to 0. C equal to D equal to 0 will give u x y equal to 0. So we cannot take C equal to D equal to 0. So we consider A plus B equal to 0. Now let us put x equal to pi. So u pi y is equal to 0 means A e to the power mu pi plus B e to the power minus mu pi times C cos mu y plus D sin mu y equal to 0. Again C equal to D equal to 0 is not possible, so we take this equal to 0. Now from this equation B is equal to minus A, if you put B equal to minus A in this, what we will get? A times e to the power mu pi minus e to the power minus mu pi equal to 0. Okay. Now if A is equal to 0, then B equal to 0 and we get trivial solution. Otherwise e to the power mu pi is equal to e to the power minus mu pi. Okay. So I mean to say A equal to 0 or e to the power mu pi equal to minus e to the power equal to e to the power minus mu pi. Okay. A equal to 0 gives A equal to 0 you put here, you get B equal to 0 and then we get the trivial solution. Okay. if you take e to the power mu pi equal to e to the power minus mu pi, then you get e to the power 2 mu pi equal to 1, and which gives mu equal to 0. And mu equal to 0 is not possible because we are considering k greater than 0, k is equal to mu square. So, this is not possible. So, what we do? We consider the case k less than 0, where k is minus mu square. When k is minus mu square, you put here minus mu square, d square x over dx square plus mu square x equal to 0 will give you a cos mu x plus b sin mu x as the solution. Okay? And here when you put k equal to minus mu square, you get the solution of this equation, d square y over dy square minus mu square y as c cos hyperbolic mu y plus d sin hyperbolic mu y. We can write it as c cos c e to the power mu y plus d e to the power minus mu y also. Okay? This part can be written also as c e to the power mu y plus d e to the power mu y. We can write either one, either this one or this one, because we know that e to the power theta is equal to cos hyperbolic theta plus we have cos hyperbolic theta equal to e to the power theta plus e to the power minus theta by 2, and sin hyperbolic theta equal to e to the power theta minus e to the power minus theta by 2. Okay? So, corresponding to e to the power mu y, you can write if you add here, e to the power theta becomes cos hyperbolic theta plus sin hyperbolic theta, and e to the power minus theta becomes cos hyperbolic theta minus sin hyperbolic theta. Okay. So, e to the power mu y you can replace by cos hyperbolic mu y plus sin hyperbolic mu y, and e to the power minus mu y you can replace by cos hyperbolic mu y minus sin hyperbolic mu y, and then collect the coefficients of cos hyperbolic mu y and sin hyperbolic mu y. They are some constants. So, we can replace them by new constants, and we have the solution also in this form. Okay, so now what we do, let us use the boundary conditions. We are given u0 by equal to 0. When u0 by equal to 0, we will have here put x equal to 0. So, this will be a plus this will be 0. So, a times c cos hyperbolic mu y plus d sin hyperbolic mu y. This is 0 for all by. Okay. So, that will mean that either a equal to 0 or c equal to d equal to 0. C equal to d equal to 0 will give this part corresponding to this capital Y as 0, and therefore, u x y will be 0 for all x and all y. So, which will be a trivial solution. So, we consider a equal to 0. So, u0 by equal to 0 gives a equal to 0, and then what will happen is that this equation will reduce to u x y equal to b sin mu x into c cos hyperbolic mu y plus d sin hyperbolic mu y. This b can be multiplied inside. bc can be replaced by new constant, and bd can also be replaced by new constant, and we can write sin mu x times e cos hyperbolic mu y plus f sin hyperbolic mu y. Now, let us use the boundary condition u pi y equal to 0. When u pi y equal to 0, what we will get? Sin mu pi times e cos hyperbolic mu y plus f sin hyperbolic mu y, okay, equal to 0. So, again e and f are both zeros, or sin mu pi equal to 0. E and f both if we take 0, then u x y will be 0 for all x and y. So, we take sin mu pi equal to 0, and sin mu pi equal to 0 gives you mu pi equal to n pi. Okay. So, we can cancel pi and we get mu equal to n, where n takes values 0 plus minus 1 plus minus 2 and so on. Okay. So, thus we get u x by as sin n x corresponding to each value of n. We will have a pair of constants e and f. We can write them as e n and f n. Now, here we shall be considering only positive integral values of n, not n equal to 0 or negative integer values of n. N equal to 0 if you take, then what we will get? Mu will be 0, but k is equal to mu square, okay, and k is less than 0. So, mu can never be 0, and therefore, n is equal to 0 is not admissible. But when if you take n equal to minus 1, minus 2 and so on, then we know that sin minus theta, okay, is equal to minus sin theta Okay. So, that negative n negative value of n will not add any another solution, only the constants will be changed, they will be replaced by new constants. So, negative values do not give any new solution, therefore, we only consider n equal to 1, 2, 3 and so on. So, when for each value of n equal to 1, 2, 3 and so on, u n x y, this could be u n x y is equal to sin n x E n cos hyperbolic n y plus f n sin hyperbolic n y. Now, we know that u x pi is equal to 0, this is given to us. The condition u x pi equal to 0. Okay. So, this condition we use, and so put x by equal to pi here. When by equal to pi, we get sin n x times E n cos hyperbolic n y n pi plus f n sin hyperbolic n pi equal to 0, which means that this is equal to 0. So, we can write E n cos hyperbolic n pi equal to minus f n sin hyperbolic n pi, and therefore, f n over E n will be equal to minus cos hyperbolic n pi over sin hyperbolic n pi. Now, let us write this equation u x. Now, in order to include the boundary condition u x 0 equal to sin square x, we need to consider a linear combination this sigma n equal to 1 to infinity sin n x E n cos hyperbolic n pi n by plus f n sin hyperbolic n y. Here we can make use of this relation f n over E n equal to minus cos hyperbolic n pi over sin hyperbolic n pi here, and then it will become okay. So, let me write what we have here. This is u x by, if you use this u x y equal to sigma n equal to 1 to infinity E n sin n x times, we want to replace f n by E n. So, we take E n outside, and then we have cos hyperbolic n by minus f n over plus f n over E n. So, f n over E n will be minus cos hyperbolic n pi over sin hyperbolic n pi multiplied to sin hyperbolic n y. Okay. So, this is what we have, and therefore, we just have to evaluate this constant E n. For that, we make use of the condition u x 0 equal to sin square x. So, when you put y equal to 0 in this, what you get u x 0 is equal to sigma n equal to 1 to infinity sin n x into E n, and you put y equal to 0. Y equal to 0 means cos hyperbolic 0, cos hyperbolic 0 is 1, and here what we will get sin hyperbolic 0 is 0. So, we will get E n into 1. Okay. And this is Fourier half range Fourier sine series. Okay. So, what we do, we multiply both sides by sin m x and then integrate over 0 to pi. So, what we have this one. Okay. So, we have u x 0 is sin square x. So, sin square x into sin m x integral over 0 to pi dx. Okay. Sigma n equal to 1 to infinity sin n x 0 to pi into sin m x dx multiplied to E n. So, we multiply both sides by sin m x and then integrate over the interval 0 to pi. Now, this I can write 0 to pi sin square x can be written as 1 minus cos 2 x by 2 into sin n x sin m x dx equal to sigma n equal to 1 to infinity. We can multiply and divide by 2. So, 1 by 2 sin n x sin m x dx, we can write that as cos m minus n into x minus cos m plus n into x into E n. Now, we integrate this over 0 to pi dx. So, we will integrate this. So, we will have 1 by 2 the integral of sin mx will be minus cos mx divided by m 0 to pi, and then we have minus 1 by 2 sin mx into cos 2x. So, again 1 by 2 integral 0 to pi, we have 2 sin mx cos 2x. So, we have sin m plus 2 into x plus sin m minus 2 into x dx. This is the left hand side, okay, equal to 1 over 2 sigma n equal to 1 to infinity integral of cos m minus n into x will be sin m minus n over m minus n into x over m minus n, assuming that n is not equal to m, minus sin m plus n into x divided by m plus n 0 pi into en. So, here we are taking n not equal to m, n is not equal to m. So, that the division by m minus n is defined, right. Now, this is how much 1 by 2 we have 1 minus cos m pi by m, okay, and minus 1 by 4, here we will have minus cos m plus 2 into x divided by m plus 2 0 to pi, and here we will have minus cos m minus 2 into x divided by m minus 2 0 to pi. So, for this to be able to divide the cos cosine function by m minus 2, we need to consider m not equal to 2. So, m is not equal to 2 here, alright. Now, this is what okay. So, 1 by 2 sigma n equal to 1 to infinity sin m minus n. Okay, now, when we put the limits, sin m minus n into pi is 0, sin m plus n into pi is 0. So, the whole thing is 0. When you put 0 for x and 0 for y, this is again 0. Okay. So, what we get? So, we can say that sigma 1 by 2 sigma n equal to 1 to infinity. Okay, this quantity becomes 0. So, we can say that we have to consider m equal to n. Okay, this quantity inside the bracket becomes 0. We cannot determine this thing en. So, let us put m equal to n. When we put m equal to n, what we get? 1 by 2 sigma n equal to 1 to infinity m equal to n. Okay, m equal to n means 1 minus cos 2 mx divided by 1 minus cos 2 mx, okay, integral 0 to pi dx and E m, because we are taking only m. So, this will be only this. Okay. So, 1 over 2 0 to pi 1 minus cos 2 mx dx into E m, this is what we will get, and we are first calculating for m not equal to 2. So, we will have integral here x minus sin 2 mx divided by 2 m 0 to pi, this is half here. So, E m, what do we notice? At x equal to pi, we have pi by 2 into E m. This term becomes 0 at pi, and both the terms become 0 at x equal to 0. So, we have 1 by 2 pi into E m, m is not equal to 2. And what will happen here? We have here 1 by 2 1 minus cos m pi. So, 1 minus 1 to the power m divided by m, and here we will have minus 1 by 4 1 minus minus 1 to the power m plus 2 divided by m plus 2. Okay. And here what do we have? 1 over m minus 2. Okay. 1 minus 1 to the power m minus 2 over m minus 2. Okay, this is what we get when m is any integer other than 2. So, here what will happen is that you can see if m is even, what we get, m is even, then this is 1 minus 1, so 0. M is even means m plus 2 is even, so this is also 0. When m is even, 1 minus 1 to the power m minus 2 is 0, so this is also 0. So, let us take m to be odd. Okay, m equal to 2 case we will resolve later. So, let us take m equal to odd. When m is odd, when m is even, not equal to 2, okay, we get left side is 0. So, em equal to 0. Okay, when m is odd, okay, we can get this is 1 by 2, 1 minus 1, so we get 2 upon m minus this will be 1 by 4, 2 upon m plus 2, so 2 by 4 m plus 2, okay, and here we will get 2 upon m minus 2. This 1 by 4 have to be multiplied to both here also, okay, because this is 1 by 4, we are integrating this, this is this integration we are doing. So, minus, and this will be also minus, because we have minus sign here, so that minus times this we shall have. So, this is minus we will have, okay. So, we have minus here, okay. Then what we will have here, 2 over 4, okay. So, this is also 1 over 4 and with negative sign. So, minus 2 over 4 m minus 2 equal to 1 pi by 2 into en. Okay. This regarding m is odd, okay. This we can simplify and get the value of em for odd. Let us look at the case m is equal to 2, the case m equal to 2 separately. So, m equal to 2 means pi by 2 into E2, okay. M equal to 2, let us put here in the left hand side, then we will have integral 0 to pi 1 minus cos 2x by 2 into sin 2x. Okay. So, this will be equal to 1 by 2, integral of sin 2x will be minus cos 2x by 2, 0 pi, and then sin 2x cos 2x is 1 by 2 sin 4x. So, we will have minus 1 by 4 minus cos 4x by 4, 0 pi, okay. And what we get, 0 pi, if you put here cos 2 pi is 1, cos 0 is also 1. So, they will be same, okay. They will be same, and therefore, this value will be 0, and similarly this value will be 0. So, E2 is equal to 0. So, this implies E2 equal to 0. So, hence En is 0 when n is odd, when n is even, sorry, n is even, and En is equal to this quantity. Em gives you, you can find the value of Em from here for m is equal to odd, and so that you can get En, okay. So, Em comes out to be this, okay, and you can then put the value of Em here, okay, in this series where we have written the series 0 to pi, we wrote, yeah, in this series we have written, okay, n equal to 1 to infinity sin nx En times this. So, here En becomes 0 when n is even, only when n becomes odd we get the value of En, and En is equal to minus 8 over pi n into n square minus 4. So, that value you put in that series, we get the result, okay. And then this can be simplified, sin hyperbolic n pi into cos hyperbolic n by minus cos hyperbolic n pi over sin hyperbolic n pi, that can be written in this form. sine hyperbolic and pi minus pi. So this is how we get the solution of this. Now let us consider Poisson equation on a rectangle. Let us consider the equation, Poisson equation minus del square u x by equal to f x by, where x by belongs to G. G is a rectangle 0a cross 0b. This is x by equal to 0, by equal to 0, this is by equal to b, here is x equal to 0, x equal to a. Okay. So we are considering the Poisson equation on a rectangle. Okay. G denotes the interior of this rectangle, this is G, okay, and this boundary consisting of 4 sides is of the rectangle is d del G. Okay. So boundary consists of the 4 sides of the rectangle. Now first we will solve the eigenvalue problem, minus del square b x by equal to lambda b x by, where x by belongs to G, and we will consider the Dirichlet boundary conditions, that is b takes value 0 on the boundary of G, that is on the 4 sides. So b x by equal to 0 on the boundary of G means b 0 y equal to 0, b this one b 0 y equal to 0, then b x 0 equal to 0 corresponding to this side, and then b a y equal to 0 corresponding to this side, and b 0 b x b equal to 0 corresponding to this side. So these are 4 boundary conditions which come from this Dirichlet condition b x y equal to 0. Now we consider the Dirichlet boundary condition. In the case of Dirichlet boundary conditions, this lambda is strictly positive. Now let us put the bx by the solution, let us find of this equation. Okay. So let us put bx by equal to px into q by, function of x into a function only of y. Since bx by equal to 0 on x by belongs to G, we have okay. Now you can see b 0 y equal to 0 gives you p 0 equal to 0. Okay. b a y equal to 0 gives you p a equal to 0, and b x 0 equal to 0 gives you q equal to 0. b x b equal to 0 gives b t v q b equal to 0. Now substituting this bx by equal to px into q y into equation 2, this equation, okay, what we have is this minus p double dash x over px minus q double dash by over q by equal to lambda. If we assume that now minus p double dash over x over px depends only on x, minus q double dash by over qy depends only on y, so both must be a constant. Okay. Why? Because you can see like this, this quantity you bring to the other side. Okay. Lambda is a constant, so you can write minus p double dash x upon minus p x equal to lambda plus okay. Now this is a function of x alone, this is a function of y alone. Okay. Lambda is a constant, so left hand side depends on x, right hand side depends on y, and therefore both must be equal to a constant. This must be a constant and this must be a constant. Okay. This is a constant means q double dash by minus q double dash by over q y is a constant. So let us take this equal to mu, this equal to nu. Okay. Then we can see that mu plus nu equal to lambda. Okay. So mu plus nu equal to lambda. Now this leads us to 2 eigenvalue problems, minus p double dash x equal to mu px minus q double dash by equal to nu qy. Okay. And the boundary conditions on this eigenvalue problem are p 0 equal to 0, p equal to 0. We know that when you solve this problem, p double dash x minus p double dash x equal to mu px, you get these equations, d square plus mu. Okay. D square plus mu px equal to 0. Okay. So px, so this means that m square is equal to minus mu. This gives us 2 complex roots, because mu we are taking here as positive. Okay. So px will be equal to a cos root mu into x plus b sin root mu into x. Okay. So, what will happen? P0 equal to 0 will give P0 equal to 0 will give A equal to 0. So, Px will be equal to B sin root mu into x. Okay. And therefore, B can be taken as 1 without any loss of generality. So, Px will be equal to sin root mu into x. So, eigenvalue is mu. Okay. For this eigenvalue problem, minus p double dash x equal to mu px, eigenvalue is mu. So, eigenvalue is equal to mu. Okay. And okay, we use this other condition, p a equal to 0. P a equal to 0 means sin root mu a equal to 0. Mu a equal to 0. So, root mu is equal to n pi by a. Okay, so mu equal to n pi by a ka whole square. So, we get in place of n I am writing j. So, j pi by a ka whole square we get, and the eigen functions are sin root mu is n pi, or you can say j pi by a. So, sin j pi x by a we get, and these sine functions satisfy the orthogonality property, that is integral 0 to a pjx pkx dx is equal to 0 whenever j is not equal to k. They are orthogonal, also they are complete, that means 0 to a pj square x dx is non-zero, we can calculate its value. Similarly, the other eigenvalue problem, this one minus q double dash by over q by equal to b with boundary conditions q0 equal to 0, qb equal to 0 gives us the eigenvalues vk equal to eigenvalue nu k equal to k pi over b whole square, and qk by eigenfunctions qk by equal to sin k pi y over b. These eigenfunctions again satisfy this orthogonality property and they are complete, okay, on the interval 0 b. Thus, the eigenfunction new eigenfunction vjk x by is pjx into qk by, and eigenvalues are lambda equal to mu plus nu. We have the eigenvalue is here, this is the eigenvalue lambda. Okay, you can see here lambda is the eigenvalue for this eigenvalue problem, and lambda is the sum of the eigenvalues of the two eigenvalue problems. So, lambda is equal to mu plus nu. So, lambda equal to mu plus nu gives you lambda jk equal to mu j plus nu k for j equal to 1 2 and so on, k equal to 1 2 and so on. The inner product of f and g is defined as over the double integral over g f x by g x by dy dx dy. So, inner product of bjk with bj dash k dash is 0 to a 0 to b bjk x by bj dash k dash x by dx dy. Now, bjk is what? Bjk is equal to pjx qky. So, we have 0 to a 0 to b pjx into qky. This is what we have for bjk, and similarly for bj dash k dash we have pj dash x into qj dash by qk dash by, okay, into dx dy. We can then separate the integrals 0 to a pjx into jk q pjx into pj dash, because they are orthogonal, no? They are orthogonal. Okay, that property we satisfy. So, we have pj dash x dx into 0 to b q ky into qk dash y dy. So, they are zeros, okay, 0 into 0 whenever j is not equal to j dash, k is not equal to k dash. Now, for any function f x y, the Fourier coefficients f j k are given by f j k equal to f v j k over b j k b j k. F v j k is in the inner product of f with b j k. So, 0 to a 0 to b f x y b j k are p j k q k by. So, q k by dx dy. and this bjk is the inner product of bjk with bjk, and that we have already seen. Okay, this is bjk. So here in place of j dash k dash we will write jk. Okay, so we will have 0 to a pj square x dx and 0 to b qk square y dy. So this is what we have, and so then fxy is given by sigma j equal to 1 to infinity, k equal to 1 to infinity, fjk vjk xy. Solution of the Poisson problem. Let us we have to find the solution of the Poisson equation. Uxy can be represented as sigma j equal to 1 to infinity, k equal to 1 to infinity, ujk vjk xy by its Fourier series. We have to determine the values of ujk. So uj can have to be determined substituting this uxy series of uxy, Fourier series of uxy into this equation, minus del u equal to this one. We have this one equation, minus del u equal to fxy. We have this, okay, minus del u equal to sigma j equal to 1 to infinity, k equal to 1 to infinity, ujk minus del bjk xy, and this is sigma j equal to 1 to infinity, k equal to 1 to infinity, minus del bjk xy is equal to lambda jk bjk xy by the equation this one, this equation. Okay, so we have this, and this is equal to fxy. Now we ujk, lambda k, r, jk are the Fourier coefficients of the function fxy. They are the Fourier coefficients of the function fxy, and ujk into lambda jk therefore are given by the quotient of the Fourier coefficient of the inner product of f with bjk over inner product of bjk with bjk. So ujk can be determined as lambda jk inverse into this. Now let us solve the Poisson equation for the case fxy equal to 1, we take x a equal to 2, b equal to 1. So we are taking this rectangle, this is x equal to 0, this is x equal to 2, this is y equal to 0 and y equal to 1. Okay, and f equal to 1. So in that case mu j will be j pi over 2 whole square, pj will be sin j pi x over 2, we are taking a equal to 2, b equal to 1, and then bk will be k pi whole square, qk pi will be sin k pi y. Okay, and then the eigenvalues lambda jk are mu j plus qk. So j square pi square by 4, k square pi square. Eigen functions bjk are pjx into qky. So this into this. Now bjk into bj dash k dash. Okay, bjk we can find. bj dash k dash is equal to 0 whenever j is not equal to j dash, k is not equal to k dash. So inner product of bjk with bjk. This is equal to integral 0 to a, 0 to a means 0 to 2, pj square x dx, okay, and then 0 to 1, okay, qk square by dy. So we can put the value of pjx as sin j pi x over 2, qk by as sin k pi y, and evaluate this. This comes out to be half, and then f bjk will be equal to f bjk will be equal to inner product of f with bjk. Okay, inner product of f with bjk. This one, integral over 0 to a, 0 to b, fx by pjx qk by dx dy. This we can find. This comes out to be 4 over j pi into 2 over k pi if j and k are odd, 0 if j and k are even. We know the values of bjk. Bjk is pj x into qk by, and f is fxy equal to 1. Okay, fxy equal to 1. So we will get the value of this, and then ujk can be determined. Ujk is equal to lambda jk inverse, lambda jk inverse f bjk over bjk. Okay, both j and k are odd, which implies uxy equal to this expression. Uxy is equal to this. We have this expression. for any function f x y we had this. So, we have for the function u x y we can find j equal to 1 to infinity, k equal to 1 to infinity the series. So, we get this u x y equal to this expression. So, this is how we solve this problem. With this I would like to end my lecture. Thank you very much for your attention.